Hello and welcome. In this video, we're going to tackle another mechanics hard question. This question is from the June 2018 paper, and it's a moments question. It's a tough one, so let's try to read it and approach it together. So first of all, I always like to start by reading what's happening. So it says, a uniform wooden beam AB. So the word uniform tells me something. The word uniform is a keyword telling me that the weight of the beam, because this person probably has a weight, okay, and there is also the weight of the beam itself. Type, where is the weight of the beam itself? Is it here? Do I put it here? Where do I put it? The word uniform solves this problem for me. It tells me that the weight of the beam is in the center of the beam, or exactly in the middle. So the center of mass of the beam is exactly in the middle. So if this is 4 meters, I will have my weight exactly bang on in the middle. Over here is going to be my weight force. Okay, and it has a mass of 20 kilograms. So the weight is going to be mass times g, so 20 g. And length 4 rests in equilibrium. Okay, here, since this is in equilibrium, we know two things. First, that sigma forces in opposite directions are equal to 0, or sigma forces equals to 0. Second thing is that sigma moments equal 0. No net moment, no net force. This makes an equilibrium. These are the two essential conditions to be there when I can say my system is in equilibrium. If one of them is not there, then my system is no longer in equilibrium. So this is a huge word that tells me a lot. These keywords are super important. And by the way, I have a full mechanics course on Udemy that's super useful. Please feel free to go check it. I go through every single keyword and what does it mean and how to interpret it. And if you need, you can send me an email and I'll send you a discount code for the course. So let's continue reading the question. It says that it rests in equilibrium in a horizontal position on two supports, support C and the other support is D, and it gave you the dimensions or the locations of these two supports. A boy of mass 60 kilograms stands on the beam at the point P, where AP is 3 meters. So I have this boy, he has a mass of 60 kilograms, so obviously he'll have a weight 60 G over here acting down, and it's 3 meters from A. The beam remains in equilibrium in horizontal position by modeling the boy as a particle. As a particle means that all of its mass is concentrated into one point. And the beam as a uniform rod. Uniform, we talked about it. Weight of the beam is in the center. And the word rod tells me that it only has one dimension. So it has only length. It's not thick on that way, and it's not super... so it's not thick and it doesn't have like a 3D dimension. This is understood by the word rod. Part A tells me, find in terms of G the magnitude of the force exerted on the beam by the support at C. So always in moments questions, what you need to do is always draw all your forces, similar to a free body diagram. So we draw all our forces that are acting on the beam. We have the weight of the beam, which is 20 G, we already drew that. The weight of the boy, 60 G. And we have the reactions of the two supports. Whenever we have supports, we will have reactions. So let's call this reaction RC. And we'll have another reaction over here, which is RD. Okay, now the question wants me to find those two reaction forces in terms of D. So what I'm going to use is I'm going to use the fact that we have sigma moments equals 0. This tells me that the anti-clockwise moments are going to equal the clockwise moments about any point on the beam. It means that if I'm taking any point, let's say this point, and I'm calculating the moments about it, any force that's going to cause anti-clockwise moments, or the total forces that are going to cause anti-clockwise moments, or the total anti-clockwise moments are going to equal the total clockwise moments at any point. So this point, that point, here, over there. So I can feel free to choose any point that I want, but however, I'll teach you some ways in order to choose a point smartly that's going to make your life way easier. So over here, we say, we want first to find the reaction at C. as I told you, I'm gonna probably do an equation where I'm going to get the anti-clockwise moments and equate them to the clockwise moments about a point. The question here is, which point do I choose? When I come and look here, I can find that I have two unknown forces. What I can do is I can take, let's say, a point here and then get the moment from each force. So the moment from RC is going to be this way about this point. Take care that when I'm talking about point A, RC is going to have an anti-clockwise moment, okay? The same RC, let's say if I'm talking about point B, the same force is going to have a moment that way about point B, so it's going to have a clockwise moment. So don't ever memorize this force, okay, this force is anti-clockwise. No, it depends on which point are you taking your moments about. So again, I was giving you an example of taking about point A. I'm going to have an equation with two unknowns. Is there another simpler way that could ease my calculations? Yes. By knowing the fact, let me take the point actually as green color. By knowing the fact that, for example, if I took the point as point D, if you come and think about the reaction force D, what is the perpendicular distance to this point? It's 0. So that means that we know that moments equal force times distance. Yeah. So if the distance is 0, the moment caused by the reaction D, the reaction force D about point D is 0. And in order to visualize this, I'm gonna give you a simpler example. Let's say I'm gonna take, let's zoom in. Let's say I'm gonna take my point as point B over here. So what is going to be the moment due to force RD? Super easy. You're gonna tell me moment. So you're gonna tell me that moment is going to equal the force, which is RD, multiply the perpendicular distance, which is 0.4. I'll tell you yes, that's correct. What if I took the point other than point B? I'm gonna take it, let's say over here. So you're gonna tell me again, let's say that this distance now is not 0.4, it's gonna be shorter, let's say 0.2. So your moment is going to equal RD times 0.2. What if I keep going towards D until the perpendicular distance is actually 0? This shows you that my moment now, so now if I take my point actually at point D, there will be no perpendicular distance to the point from the force. So the perpendicular distance is 0. So my moment is going to equal RD times 0. So my moment due to RD is going to equal 0. That way, I eliminated RD from my equation. I eliminated an unknown, and just from one single equation, I can get the other unknown. So let me show you this practically. I hope it made sense, but I think here is gonna make even more sense. So let's say we are going to take moments about point D. Okay, I know the anti-clockwise moment is going to equal clockwise moments. So moments about point D. First of all, I like to go from the furthest force and then going inside. Okay, so I'm gonna do, first of all, let's see RC. What's the moment due to force RC about point D? Is going to be the force multiply the perpendicular distance. So what's the distance from here up to here? We can calculate it by, we know that this whole distance is 4 meters. Okay, so this distance up to here is going to be 4 minus 0.4, so it's going to be 3.6 meters. I know if this whole distance is 3.6 and this beginning distance is 1.6, if I do 3.6 minus 1.6, that's going to give me 2, and it's going to leave me with this distance that I want. So I know that this distance over here is going to be 2 meters. So this distance is 2 meters. So RC multiply 2. Okay, what direction is this moment? RC is going to produce a moment like this. If I pin my beam at point D, what I like to do is actually put my finger on point D and try to lift from the point C. How is my rod going to rotate? Obviously, it's going to rotate this way. So this is a clockwise moment. Okay. Do I have any other clockwise moment? I don't think so, because this 20g looks like it's going to cause the rod to move this way. This 60g is also the same thing. And this RD, we said it's not going to contribute any moments, so it's going to become 0. So that's it. That's it for my clockwise moments. I'm going to equate this to the anti-clockwise moments, which are going to be the 20g multiply this distance over here. What is this distance? Okay, we know, let's try and think about it. So we know that from here up to my 20g is 2 meters because it's exactly in the middle. Half of 4 is 2. Okay, now what I can do is I can say that also this distance, this whole distance was 4 minus 0.4, so it's 3.6. I know this is 2, so this is also 2 meters. So what I can do is I can take this 2 meters and subtract this part, subtract 0.4. So I'm going to be left with 0.6. So this distance from the 20g up to here is going to be 1.6 meters. So the force, which is 20g, multiply the distance, which is 1.6. Now I'm done with the 20g. Let me move on to the 60g. So I'm going to add it since it's also anti-clockwise moment. So I'm going to add it to the anti-clockwise moments part of the equation. So it's going to be 60g multiply this distance over here. Okay, how much is this distance? I know that if this is 3 and the whole thing is 4, then this distance must be 1 meter, right? So 1 meter, if I take away from it this distance, 0.4, I'll be left with this distance, which is going to be 0.6. So 60g times 0.6. Over here, what I can do is I can divide 2 on every side. So RC is going to equal 20 divided 2, that is 10g times 1.6, plus this is going to be 30g times 0.6. Putting that on the calculator, and the question wants it in terms of g, so I'm just gonna keep g out of the calculation. So this is going to give me 34g, because this is going to be 16g, and this is going to be 18g. So 16 plus 18, that's going to be 34, and this is my answer for the first part. This is my answer for RC. Now, let's continue for RD. RD now is super easy. Now I'm going to make use of the fact that the sigma forces in opposite directions are also going to equal 0. So that tells me that the forces in the upward direction are going to equal the forces in the downwards direction. So RC, which is up, plus RD, which is also up, is going to equal the two forces that are acting down, which are what? Which are the 20g and the 60g. So equals 20g plus 60g. I know RC is 34g from the first part, plus RD is going to equal 20 plus 60, that is going to be 80g. So now RD is going to be simply, I'm going to move this to the other side, it's going to become 80 minus 34. That is going to give me an answer of 46g, and this is my answer to the second part. Okay? So up until now, I think we are okay. The part that confuses the students is usually this second part. So let's see how we can tackle it. So now it tells me that the boy now starts to walk slowly along the beam towards the end A. So the boy, this boy, he was moving, he was standing at point B. Now he's moving, he's starting to move towards the point A. Imagine he keeps on moving. Let's say he reaches here. There will be a point where he's going to have lots and lots of moments that this beam is going to go out of equilibrium. Imagine on the seesaw, when you stand on the end of the seesaw and you have a great force, it's going to make this whole thing rotate this way, right? It's going to make this whole thing rotate that way. So this is going to happen. So what we want to know is what distance should he walk, and what's the maximum distance should he walk that we will stay in equilibrium. This is the question in part B. So what I'm going to do in this question, actually, I'm going to draw the whole thing. Let me draw it. let me draw it over here actually. I'm gonna draw it nice and big so we can understand what's happening. So what we had is, let me actually draw it over here. We don't need this. Actually, we can put it over here as a reminder. Let me draw my beam over here so I can see and copy what's happening. So I know that I have this as my end A. I know that I will have now my boy, he's gonna be now somewhere between A and C, right? He's gonna be between A and C. Tab, how do I know that he's gonna be between A and C? Because it doesn't make sense that he's going to make the whole thing rotate if he's between C and D, right? Because if you're between the two supports, there's no way, think about it logically, there's no way that this is going to tilt. Only when you're at the end that you're gonna cause this whole thing to tilt this way. So he must be between A and C. Let's call this distance X meters. Okay. Now the next thing I have is the support at C. Let me draw it this way. So this support at C is going to have a force RC. Now take care that whenever anything changes, okay, always the reaction forces changes. Don't use the same reaction forces from the first part. Okay, so we're gonna have RC. Since it's the same boy, so his weight probably didn't change. Hopefully he didn't gain or lose any weight while moving. So we're gonna keep it as 60G. We have this as RC. What's the next thing? We have the weight of the beam, which is exactly in the middle. So we're gonna have a 20G over here. Let me draw the dimensions now. So I know that RC is 1.6 from A. So let me do this. I know that RC is 1.6 meters from A. And I know that until the weight, I know that this is exactly 2 meters. What's next is RD. So this is point C, this is point D. I'm gonna have a force over here, which is going to be RD. We're gonna talk about it in a second, okay? And I know that this distance up to D, let's do this so we can visualize. So this distance is going to be, so this whole distance is 4 meters. This distance here is 0.4 meters. That leaves this distance as 4 minus 0.4, so it's 3.6 meters. Now I'm ready to try and solve. This question actually is, the marks are not for the equations. It's not very difficult. It's not tedious. It's not hard. Actually, the equation is super easy. The marks here, or the complexity, is on the way you think, or in the way how you deduce what's happening. Right. Now we want to find the greatest distance that he can walk from P without the beam tilting, right? Without it tilting, it means that if this guy moves a little bit more to the left, yeah, we are going to start tilting. And we're going to start tilting about which point? Do you think about C or about D? We are going to tilt about point C. Why? Because probably the plank is going to lift off D and is going to look something lifting off D. So it's going to look something like this. Yeah? So it's going to become like this. So we're going to rotate about C. This is super important. Again, it's a keyword, okay? Whenever I see the keyword, or I understand from the question, because here I do not exactly see the keyword. It doesn't tell me on the point of tilting or on the point of lifting of D, or on the point of tilting about C. It doesn't tell me this, but it tells me that I want the greatest distance. And from the greatest distance, I know that this is the maximum distance I can go. And anything more than that is going to tilt, so I can deduce that it's on the point of tilting. When it tells me it's on the point of tilting, or when I understand it's on the point of tilting about C, what does that tell me about the reaction force at D? It's about to lift off D, right? Is there any reaction force? What's the reaction force at the end of the day? On your desk or anything, when you put the book is exerting weight on the desk, so the desk is pushing back up. So this is the desk, this is the book. Book is pushing down, so the desk is pushing up with a reaction force. Yeah. But what about if you hold that book and make it a little bit levitate, so it's not actually touching, it's about to lift, it's merely touching? What's gonna happen? Is this desk going to experience any of the weight of the book? No, it's not going, because you're holding it or you're about to lift it. So since it's not gonna press down on the desk, then there will be no reaction up, because it's a reaction. It's a reaction to this pressing. If there is no pressing, then there will be no reaction. Same exact scenario here. The beam is about to lift off D. So do you think about it? Is the beam exerting any force downward on D? No, it's literally about to lift. Yeah. So when it's about to lift on D, RD becomes 0. Yeah, nothing's pressing down on D, so D is not gonna have any reaction force up. So this is the greatest trick in this question, to know this. Okay, so now RD equals 0. Now I want to find the greatest distance, so I can take moments. So I'm still in equilibrium, by the way. And in this, I'm still in equilibrium, so I can still use these two things. Okay, so I'm gonna use the fact that sigma moments equals 0. And over here, since I don't know RC, I'm gonna use the same exact trick we did in the first question. I'm gonna actually take moments about C. Yeah, that way I'm going to eliminate the RC from my equation, because when I multiply RC times the distance to C, which is 0, is gonna give me 0, and I will not have an RC in my equation. I will not have an unknown I can solve straight for what I want. Yeah, there is another option here, is to say that, okay, I can use the fact that sigma forces equal 0, so sigma forces up equal forces down. So RC, which is up, is going to equal the total down. So RC is going to equal 60 plus 20g, so RC is 80g. And then you can take moments about, let's say, A, for example. Now you have RC you can solve. However, I like to take as little as steps as possible to make it more efficient and to gain as much time as I can. So again, let's take moments about C, knowing that anti-clockwise moments are going to equal clockwise moments. How many forces do I have here? RD is cancelled, خلاص, it's already 0. RC, I'm not gonna have any moment effect, since I'm taking my moments about the point that the line of action of the force passes through. Okay, since the force RC passes through my point, it will not have any effect, and I've talked about this multiple times in this video. So I only have the effect of the 60g and the 20g. So let's see how we can do it. The 60g is going to create a force. Imagine you're pinning down the beam at point C and you're pulling it down from this direction. It's going to have an effect like this. So it's going to have an anti-clockwise moment. So let's say that the moments due to the 60g is going to be the force times the distance. So force is 60g times perpendicular distance, which is basically this green distance over here. This green distance, okay? This green distance is nothing but 1.6 minus x, right? So I'm going to multiply by the distance, which is 1.6 minus x. That is the anti-clockwise moments. Do I have any other anti-clockwise moment here? No. The second moment, the second force is going to create actually a clockwise moment. It's going to create a moment in the opposite direction. It's going to be 20g multiply this distance over here. Okay, what's this distance? It's going to be 2 meters minus 1.6 meters. So it's going to be 0.4 meters. So this is times 0.4. So let's delete this. Yeah, so over here what I can do is I can cancel a g from everything. I can say that 60 times 1.6, that is 96, minus 60 times x is 60x, equals to 20 times 0.4, that is going to be 8. I'm going to move this 60x to the other side, bring the 8 here. It's going to be 96 minus 8 equals 60x. So divide both sides by 60. X is going to equal 96 minus 8, that is 88, answer over 60. So my x is going to be around 1.4667 meters. So now this is x. Yeah, now I basically I just have one final step, because the question here doesn't tell me we want the distance from A to the point where the boy is going to be standing. No, it wants the distance that he can walk from P. So the boy initially, if you remember, he started somewhere here, yeah? And we call this point P, and this point was 3 meters. 3 meters from the end, yeah? So it's 3 meters. Now, what I want is the distance that he walked. The distance that he walked is going to be basically this green distance, right? Because he walked from here all the way up to there. So this is the distance that I'm interested in. Super easily, I can see that this whole thing is 3 meters. My x, I just got it, so it's going to be basically 3 minus x, or it's going to be 3 minus 1.4667. This is going to give me an answer of 1.53 meters, and this is the final answer to this question. Honestly, moments questions can either be super tough or super easy when you know and you have enough experience doing what you are supposed to do. Again, this is explained thoroughly in my course. Feel free to check it out in the description, and please don't forget to like and subscribe. It helps a lot, guys. If you're not subscribed, if you didn't like, if you didn't comment, please go ahead and do that right now, as it keeps me going and making more videos for you guys. Anyways, thank you so much for watching, and have a nice day.